Hi, this is Ed from CNC Explorer, and I'd like to try to explain the relationship between chip load and feeds and speeds. Um, and I hope this comes across. I thought about it a little bit, try to how to present the relationship between feeds and speeds and RPMs and chip loads, and we'll give it a show and see how it goes. So I have a diagram here of what's known as a conventional cut. In woodworking, CNC woodworking, conventional cut is probably the predominant technique. The alternative is what's called a climb cut. I'll just bring up a picture of that. A climb cut, it's going to be more for machining metals, and it gives you a cleaner surface if done properly. The big difference between the two methods are the chip load and the amount of chip you're digging away as the cutter cuts into the material is maximum at the beginning and thins out over time. Or if we look at a conventional cut, it's starting thin, ends up at the maximum at the exit point. All right, so there's a couple of forces, or I should say directions. So we have a direction of the router milling, and that moves up. Sorry, there we go. Okay, so as the router moves down your material, you also have a rotating cutter. So when there's a balance, or I like to say a ratio between the RPM of the spindle and the momentum and direction of the milling, um, you end up creating what's known as a slice or chip load cut into your material. I'll represent that as a red stripe. So it starts thin, ends up thick on this conventional cut. And the manufacturers design their cutters for an optimum chip load width that you're going to cut on each tooth as it spins around. So that's known as a chip load on the cutter. So you make a slice through, and the momentum is always forward while it's spinning. And so the next time through, oops, the next time through with the cutter, you're starting again at the narrowest width, and as the cutter rotates and moves in, you notice there's a offset on the position as we move around the rotation. And finally, we come through to the exit point of the cut, and we've now cut another swath, another chip load. And this continues as we move down our material until we reach the end of the cut. So this results in an optimum cut. We are putting a minimum amount of stress on the cutter, And we're also making a clean cut, and the chips are being pushed out as the cutters exit the material, and they carry heat from the cutting operation. So you always want to make sure that you're ejecting chips, and you want them to be not powder, but real chips of the width that you're trying to get. Now this all works great, but let's say we're actually running the feed rate too fast for our RPM. All right. And I'll represent that by we're actually now we're gonna still start at 0, but now we're moving in too fast and we're cutting more and more material. And by the time we exit, we're cutting quite a deep cut. Now this is not optimum. There's a couple of reasons why it's not. The cutter wasn't designed to make this width of a cut, and you may actually be driving in further than the cutting edges on the tooth. Never a good thing. And we are putting pretty high stress load on the cutting teeth. Now you can imagine that as it rotates, a couple things are going to happen. More force is going to be required to make this cut because you're cutting a much deeper, wider cut. The milling tool is going to either try to deflect in, or it's going to try to pull material from its clamping. So either case, you're going to have potential unwanted movement, and which leads to chatter, and also leads to poor cutting, poor surface cutting. Now you can do this kind of a cut to a point if you really want to push your material during moving. It's probably not optimum, but it can be done. You've got to make sure that your stick out in your bit is very short, so the bit does not deflect very much. And you want to make sure your material is well clamped so it doesn't move on you. The material, the end bit deflecting, well, we can think of it as like a ringing. So you can imagine now that as you're cutting your material and you exit, it's going to release the stress on the bit until it starts digging again. So the deflection on the end mill is going to go back and forth, which is a classic example of chatter. Now the opposite condition that I want to talk about is chip. So if you're running too slow for a given RPM, you're going to set up a condition what we call rubbing. So we're only cutting now a very narrow chip width, and the cutting edge on a microscopic level is really kind of rounded off. And if it's a bit that's a little bit worn, the situation gets even worse. So instead of shaving a nice chip, you're actually just going to be kind of plowing through the material. And the material gets kind of churned up inside on the material. It's hanging around for the next revolution. It doesn't get ejected. Heat builds up, cuts back on the life of the tool, makes for a poor cut. It's not a very good situation at all. And it's something that you really need to avoid. Now, the convention for most cuts is that we should always be cutting at least a mil of chip load. The CNC Explorer app limits the minimum calculated chip load to be 1/1000th of an inch, 1 mil, so that we never get to the point where we're going to do an excessively small cut. So this situation with a very narrow, less than 1/1000th of an inch cut, will never allow this to be calculated. It's always going to be the normal cut of, 1/1000th of an inch, which is a normal cut. So probably going to make another video down the road talking about shatter. And this video, I hope it explained a little bit about the relationship between your feed rate and the width of cut. I don't think that's normally understood, and why it's really important to make your ratio between your RPM of your spindle and the rate you're feeding through your material to be in balance so that you can make a proper cut. So until next time, thank you for watching. This is Ed, CNC Explorer.